So in this video, we'll explain how the intrinsic trade-off that we observed in the longest chain protocol between security and scalability can be resolved. So the question we left over from the last video is whether the trade-off we observe is a fundamental one or is it something specific to the longest chain protocol. So what we discovered is that this trade-off is not fundamental. To break this trade-off between security and scalability, the key observation is to observe that the functions of the blocks of 1, entering transactions in the ledger, and 2, confirming or voting for previous blocks, should be decoupled. So the way we decouple it is that we introduced multiple types of blocks. So let's start with the longest chain. And now we introduce a second type of blocks. Okay? And these second type blocks are shown here blue. And they are each maintained by a different chain, which we call voting chain. And the functions of the blue blocks is to vote for the green blocks which carry the transactions. So now you can see that the functioning of voting and entering transactions are decoupled. And by having many of these voter chains, each of which is in the longest chain, one can confirm the green blocks very rapidly because there are many votes going on very fast. On the other hand, each of the voting chain, the blue chain, is growing rather slowly so that there's very little forking, thus maintaining the security. Now this allows us to improve vastly the confirmation time. Instead of waiting for many blocks growing slowly on a single chain, we have now very fast confirmation. However, this does not improve the throughput because the throughput is still limited by the green chain, which is growing rather slowly to maintain the security. So to improve the throughput as well, one can now apply this principle of decoupling to move the transactions into a third type of blocks, which we call transaction blocks. These transaction blocks are separate from the green blocks, which now only has the purpose of proposing. The transactions themselves are actually carried by the transaction blocks. And when a green blocks appeared, they will form reference link to the transaction blocks that are available at that moment and bring them into the ledger. So this way, we can increase the throughput of the system by having many transaction blocks while keeping the growth of the green blocks relatively slow, the proposal block very slow. And so what we achieved is a decoupling between security and vertical scalability. So here, the blue blocks are the voting blocks. They maintain the security, whereas the transaction blocks on the left are responsible for vertical scalability. Why do we call it vertical scalability? It's because now we can increase the transaction blocks rate to as high as the computing and communication capability of the participant nodes can afford. So the trade-off between security and scalability that we saw in the longest chain protocol is now completely resolved because of the decoupling. Now, what you can think of is that we're taking a single block tree and we're factorizing it into 3 components: the transaction blocks, the proposal blocks, and the voting blocks. And that's why we call this approach block graph factorization. This work was done when we wrote the paper Prism, which was published in CCS, ACM CCS conference in November 2019. Now, what is still missing is how to achieve horizontal scalability. And that is the topic for the next video. For more information, please also take a look at our white paper, which is available on our website.